Okay, welcome back to our Calculus 3 class notes. We're now on page 37, and we're still working up towards, let me check that. We're still working up towards example, 34. We're on page 37. And we just worked out on the previous page how acceleration can be written as some constant, call it a sub capital T, in the tangential direction, which is the unit tangent vector, plus some constant a sub n in the normal direction. Instead of something times I plus something times j plus something times k, we can think of it like this, okay, which is very useful for applications. So this is what's called the tangential scalar component of acceleration, this a sub capital T, and a sub capital N is the normal scalar component of acceleration. So we worked out on the previous page how a sub capital T is the second derivative of s with respect to t, which is the first derivative with respect to t of speed. Okay, so it's just derivative with respect to t of speed, which is the magnitude of velocity. And the normal component of acceleration is kappa times speed squared, or kappa, which is curvature, times the magnitude of velocity squared. This one is really not that easy to compute. So what we'll notice is we have a relationship between a sub t and a sub n, okay? So if we can write acceleration this way, which we can, we just talked about how we can do it, then if we want the length of a squared, so that's a dot a. So in other words, it's just a sub t times a sub t, or a sub t squared, plus a sub n times a sub n, or a sub n squared. So in other words, a sub n squared can be thought of as the magnitude of accelerations squared minus a sub t squared. So once we have a sub t, we can compute a sub n quicker this way. We don't have to worry about finding the curvature and computing it this way. So a sub n is the square root of the magnitude of acceleration squared minus the square of the tangential scalar component. So the best formulas are the following. So the tangential scalar component, a sub capital T, is the derivative of speed with respect to t, or the derivative of the magnitude of velocity with respect to t. And a sub n, the normal scalar component, is the square root of the length of a squared, right? Once we have acceleration in terms of, that should be a vector, by the way, of course. Put an arrow over there. The length of it, once we have acceleration in terms of ij and k, I can still find the length of it and square it. Doesn't matter what components it's in, so this will be in components ij and k. Then subtract the tangential scalar component squared. Then take the square root of it. So, example 34. Without finding t and n directly, write the acceleration of the motion. So here we have a curve. This is a more complicated curve. It's only in I and j, so it's only parallel to the xy plane. Okay, where t is greater than 0, and it's in the form of we want to write it in the form of the tangential scalar component times the unit tangent vector plus the normal scalar component times the unit normal vector. So how do we proceed here? So first of all, we have r, so we find velocity by finding the derivative of r with respect to t. So derivative of cosine is minus sine t. The derivative of t sine t, I must use a product rule. So that's t times cosine t plus sine of t times 1. So that's right here. We can see that minus sine t and sine t cancel, which is helpful. When I take the derivative of sine t minus t cosine t, I get derivative of sine t is cosine t. The derivative of minus t times cosine t is minus t times minus sine t, or positive t sine t. And then cosine t times minus 1, so minus cosine t. Again, the cosine t's cancel here, so again, that's useful. So now when I take the magnitude of v, I get t squared cosine squared t plus t squared sine squared t, taking the square root, factor out the t squared. I see that's t squared times 1. This is the Pythagorean identity. Cosine squared t plus sine squared t equals 1. So I get the square root of t squared, which is just t, because t is a positive number in this case. I was told that t is greater than 0, so it's not the absolute value of t, it's just t. So what is the derivative of this with respect to t? Well, that's just the derivative of t with respect to t, which is 1. So our tangential scalar component of acceleration is simply just 1. Now, first of all, I need to use this formula right here for the normal scalar component, I need to keep going with, I found velocity, now I need to find acceleration in terms of I and j. So I take the derivative of velocity with respect to t, that's the derivative of t cosine t, so again I use the product rule. t times minus sine t right here, plus cosine of t times 1. That's in the I direction. I need the product rule again for t sine t. So t times cosine t, that's this guy, plus sine of t times 1, product rule. Okay, then I take the length of that guy and square it. So the length of that guy squared is I got to square this whole term. Then I got to square this whole term. And then I can see that some things cancel. So I just FOIL each of these. You can look at the details and see that. End up with t squared times sine squared plus cosine squared t right here. That comes out to 1. And then this is 1. So I get t squared times 1 plus 1, or just t squared plus 1. So that is acceleration squared, right? The magnitude of acceleration squared. So the normal component then is that guy minus a sub t squared, which is just 1 squared, or 1. So t squared plus 1 minus 1 is just the square root of t squared, which is t, again, because t is positive. So the normal component, the normal scalar component of acceleration, a sub capital N, is t. So my acceleration, written as the tangential scalar component times the unit tangent vector plus the normal scalar component times the unit normal vector, is just going to be 1 times the unit tangent plus t times the unit normal, and that's it right there.